Okay, so welcome. This is the video for 1.4. This is using the definitions of our trig functions. Specifically, we're going to be using those definitions to come up with our reciprocal identities. Now, a lot of you have probably encountered this. A lot of people have contacted me already and said that they have been reviewing the study plan problem, so you've probably already seen a lot of these reciprocal identities. Some of the viewing examples or the Help Me Solve It may have also mentioned that. So in that case, this should be a really easy section for you. But we're just going to very quickly derive these identities. All of these first identities, in fact, all the identities we do today are just derived from the definitions of our functions, sine, cosine, etc. Using the definitions for our functions graphed in standard position, or when our angle is graphed in standard position, the same rules apply as if this was just a regular old right triangle, opposite over hypotenuse, our sine value. That's still the reciprocal of our cosecant. The cosecant is the hypotenuse over the opposite side of our angle. So these rules still apply. So, just walking through the stuff, another example in your notes, looking at sine and cosecant, the first two I mentioned. Sine of theta is y over r. Cosecant of theta is r over y. These are the definition of reciprocals. Multiplying them together would give you 1. That's one definition of reciprocals. I think almost every algebra student I know thinks of reciprocals being a fraction flipped upside down, which is just what these are. So by the definition, either one of those definitions, these are reciprocals of one another. And we write that as sine of theta equals 1 over the cosecant of theta. You could also write it the other way. Cosecant of theta equals 1 over the sine of theta. So either way, these are both reciprocal identities of one another. They both tell us the same thing. Same for cosine and secant. Those are reciprocals, and tangent and cotangent are reciprocals. And the way I've always remembered these is this. Sine and cosecant go together. They've got the opposite letters there, just like cosine of theta and secant of theta have the opposite letters there. We got S and C, S and C. All right, silly, but that's the trick I've always used to remember which one is the reciprocal. Tangent and cotangent, those are much easier. Those are reciprocals, and it makes sense. They both mention tangent. It always kind of annoyed me. I'm like, why do we call sine and cosine? Those aren't reciprocals, but tangent and cotangent are. That's a good question. I think that actually comes from the Greek meaning of these things. Of course, I don't know Greek. I can't verify that. But I'm pretty sure these names are all Greek for the geometric representations of these functions. Like tangent can be represented as a line tangent to a circle. Sine, I think, means the opposite. I may be wrong. I don't know Greek. Seems like I should research that before just telling it. But it always bothered me. I'm like, well, why are these two not reciprocals, sine and cosine, but tangent and cotangent are? I don't know why. It's just, that's the way it goes. You got all your reciprocals there. Again, I just remember them because sine and cosecant have opposite letters, or cosine and secant have opposite letters. That was a nice little trick that I always liked to do for those. Okay. Quotient identities. The next on our list, and I'll get to what these are used for at some point. I guess I can talk about it now. It seems like you'd be wondering what are these used for. I use these first ones, the reciprocal identities, all this stuff up here. because like cosecant and secant and cotangent, I don't know any of those values. I don't know any of those standard values for, or these values for our standard angle. I only know sine and cosine, and I can, if I think about it, I can come up with the other ones. I showed you how to make a chart, and I'll review that in the coming sections. Let me review that again for you. I don't remember which section exactly it was I first covered how to make that chart. Maybe I'll make a separate video and link to that. But I derived those. I find sine and cosine using one little trick, and then I find all the other ones using these reciprocal identities, these quotient identities, and, well, really those two. Later on, we're going to use these to prove other more exciting trig identities that you actually use in calculus. You do use some trig identities there. When you're integrating, you need to do all that stuff. You need to rewrite trig functions in terms of other trig functions. And the way we do that is basically just playing around with these different identities. So I don't normally use them for calculating values like out in the wild. We're not going to have a whole lot of homework from this section because some of the problems just say, here's sine and cosine, find the tangent function using these identities. So I don't do that a whole lot, but you should be able to do it anyway. All right, so I'm sure I'll think of some other reasons just off the top of my head. Now, there are a lot of reasons to know these. In fact, every identity we're going to talk about today is actually one of our fundamental identities, and you'll need to know these things pretty well. Okay. So next on our list is the quotient identities. Quotient identities. They're called that because they have a quotient. They have division in there. And I kind of derive this thing by working backwards. I want to look at sine over cosine. Okay, I just chose that fraction. Well, I chose it for a very specific reason, but whatever. I write these in terms of their definitions. I've got y over r divided by x over r. Right? Super. Hopefully you remember your algebra rules or your arithmetic rules for calculating this. A fraction divided by a fraction. We can take this bottom fraction and flip it upside down. And we're going to multiply by so we're going to flip our r and our x, and multiply the top by that. This becomes y over r times r over x. So I just flipped this x over r. Okay. And once I've done that, then I can cancel out my r's. My r's cancel, and what do I have? I've got y over x. Right? But you recognize that, right? I hope you recognize that. That is your tangent identity. Or not your identity, that's your tangent function. Okay. So sine over cosine, if you ever know the sine and the cosine, you could, of a particular angle, you could use that to find the tangent of that angle. And vice versa. We may or may not do that. This thing definitely does work both ways. You can, if you ever have tangent, you can write that as sine and cosine. We'll do that when we get to our proof sections. We'll do that a lot. Sine and cosine will also often take and write as tangent. In fact, we'll do that in just a second here. This rule works the same for cotangent. Remember, cotangent is the reciprocal of tangent. Well, what's the reciprocal of sine over cosine, right? Sine over cosine is tangent. So the reciprocal of tangent is this reciprocal as well. It's cosine over sine. I'm normally pretty good about writing those parentheses. I try to write those in there. But cosine over sine is our cotangent. I normally try to write those parentheses every time, but sometimes clearly I forget. So that's it for that. We've got our Pythagorean identities. Now there is some notation you got to be aware of. This quirk of notation, I've got it called there. And it seems like a quirk, but there's actually a pretty good reason for it. So you have to be aware of this, that when I have something written as sine squared theta, what that actually means is I'm squaring this whole thing. Right? I'm calculating that thing and then squaring it. I'm squaring that whole function. So I've got this entire function times that entire function. The reason we don't write this over here, I guess I could write it like this. But again, mathematicians are lazy. Even I left off my parentheses a second ago. Of course, I don't think any of you think I'm not lazy, except whatever. Mathematicians aren't going to write this parenthesis consistently. I don't think anyone would. When I was learning this stuff, because it was always bothered me, I always wrote it like this. But eventually you get sick of it and everyone starts doing this. If you write it without the parentheses, that's going to cause some problems. People are going to think that this square is only applying to that angle, which is not good. It's really not good if that person is you, because then you're the one who screws up and you're going to get in trouble for it. Someone's going to hold you accountable because you're going to get doubly fussed at because the reason you made the mistake is because you couldn't adopt standard notation. I mean, it's standard notation for a reason. It helps you avoid those mistakes. Okay, so you got to know what that means. It means we're squaring that. Okay, so what we're doing, as I say, through magic here, we derive our Pythagorean theorem, or Pythagorean identity. This is actually not magic at all. There are a lot of ways to derive this. Your textbook, I believe, has a couple of ways to derive it. I want to say your textbook derives this at least once. This is your Pythagorean theorem. We've taken one side of our angle, the other side of our angle, and we know that that's set equal to the hypotenuse. What they've done is they've chosen an angle. We've chosen an angle in standard position. Can y'all see that? Yeah, there's some glare up there. We've got this angle in standard position. And remember, our y value is right there, and x. And what we've done here is we've chosen this very carefully. We've chosen our point. Let me make this larger. We've chosen our point here very carefully. And I made a big deal about how we can choose this point on our terminal side. We chose this point so that our radius here is 1. Right? So then sine is y over 1. Right? The length of this side is just it's equal to our trig function sine. Normally our trig function is equal to y over r, but in this case our r is 1. So y is y over 1, or just y. So with this careful choice of our r, this becomes a lot easier. X becomes cosine of theta. And then the Pythagorean theorem says instead of x squared plus y squared equals 1 squared, we have cosine squared plus sine squared equals 1 squared. It's just that we don't write that as 1 squared. 1 squared is just 1. So that's what is going on there. There's something tricky. I just didn't want you to worry about that. I didn't want you all to get... Of course, then I explain it anyway. I just can't help myself. But it looks like the Pythagorean theorem, right, a little bit. And it actually comes right from the Pythagorean theorem, just with a little kind of manipulation in between. So this is one of our main identities, the Pythagorean identity. I know some physicists who tell me that this is all they know, the trig. And I could see that, I guess. And there's a lot that you could pull out of this. We can also rewrite it with a little bit of manipulation. And that's what I'm going to do in the next page here, if you go into your next page in the notes. And I don't have these two memorized 1 plus cotangent squared equals cosecant squared. I don't have that memorized. Also the next one, tangent squared plus 1 equals secant squared. I don't have that memorized. I don't have the mental capacity nor the mental stamina to deal with that crap. Instead, what I do is this thing I've got written here. If you take your standard Pythagorean identity and you divide it either by sine, which is what I do first, I divide everything by sine squared, or I divide everything by cosine squared, it simplifies. And that's just what, okay, everyone's trying to get in here. Teaching class, okay. So dividing this by sine squared, I could then simplify this to this other form of the identity. So the first one, sine squared divided by sine squared, and I'll even write that. I can actually do this. I want it. So to divide everything, right? That's how math works. You do it to one part of your equation, you have to do it everywhere. Sine squared divided by sine squared. Well, anything divided by itself is just 1. Cosine squared divided by sine squared, that is your cotangent, right? Sine over cosine is tangent, cosine over sine is cotangent. And since I had 2 of these, I had cosine times cosine, sine times sine. I still got 2 of them. I've got cotangent squared. So when these are squared, this is squared. Similarly, this is squared, so this down here is going to be squared. What is the reciprocal? The reciprocal sine is cosecant. Again, I can remember that because sine, cosecant have the different letter there, S and C. So don't get confused and write cosine. And there's our next identity. Again, this is still called the Pythagorean identity. I'm not going to go through the next one. It's the same steps. I'm just dividing each one by cosine. So, again, I don't have those last 2 memorized, but if I know I'm doing a bunch of this, like, say, I'm being tested on it, or if I've got to work out a bunch of integrals, then I would do this. I think it's the movie The Cube. This mathematician is stuck in this cube where all the different rooms, there are all these different rooms in this cube, and as you go from room to room, there are different torture devices in only certain rooms, and she had to do all these integrals in order to figure out if the room she was about to go into. There are a bunch of numbers on the door. She had to do some integrals and figure out if that room was booby-trapped or not. You know, each of the possible faces of the cube had a door on it, and she should test them all, using her mathematics to do it. So I guess if I was trapped in a cube and didn't have a book of identities with me, I would derive these things using this rule here. So you should memorize these, or you should memorize how to derive them. These really all of these highlighted identities in this section. I didn't realize there was more to this section. Oh crap! I've got a bunch of. Okay. I thought I was going to be able to get this done and get out of here early. I guess not. All right. So the other thing from this section is the signs of these trig functions, positive or negative. Really, all you have to do here is look at your basic definitions. Each of these things is defined in terms of x, y, and r, and look at whatever point it is in the quadrant, or which quadrant it's in. Look at, okay, well, is x negative, is y negative, and determine if your function is negative based on that. So, for example, this first one in quadrant 3 is secant of theta positive or negative. I'm going to hold on to this thing for the life of me. Okay, so I've got quadrant 3. I don't care where, somewhere in quadrant 3 I got my angle, right, swept out in quadrant 3. let's look at a test point. It doesn't matter what point we chose there. I just want to look at the signs of that point. So I've got an x value and a y value, right? Well, over here on the left, what are all my x values? Right, here's my x-axis, here's my y-axis. Over here, all my x's are negative, right? So this is going to be a negative value, whatever that is. I don't know. It's going to be negative. And my y value, well, down here, remember in quadrant 3, my y values are going to be negative. So those are both negative. Okay. So I identified that and made this kind of funny owl-looking shape. Much better art if I draw an owl. What do y'all think? Pretty good, huh? Maybe a beak. Maybe a better beak. But anyway, my x and my y are both negative. I'm so sorry. Okay, so I've got my x and my y, they're both negative there. What is secant? Secant, reciprocal of cosine. Cosine is x over r, so this is r over x. Now, r is always positive, and we saw y in one of these other sections. But r is always going to be positive. So we know that's positive. X we saw in our little owl here, his left eye. That was our x value. We have a negative x value. So we've got a positive over a negative. Right? Positive r value, negative x value. What's positive divided by negative? That's a negative. So in quadrant 3, secant has to be negative. And that's it. Minus the drawing, this should only take you a few seconds. It's a weird drawing. I don't know if that makes it any better. Okay, moving on. Next, you can use the sign of the various trig functions to find which quadrant your angle is in. So this is kind of going the opposite. Here we found our point and use that to find where the sign of our function had to be. We can also go the other way, and that's what we're about to do. So this example I've got here, example 2, identify the quadrant or quadrants. It could be multiple quadrants. So that sine is negative and cosine is positive. Cosine is positive, y is negative. That's all it means. Less than 0 means it's negative. Cosine greater than 0 means it's positive. Okay, but what are each of these? Sine, y over r. The only way sine can be negative is if y is negative. Right? Since this is always positive, the only way I can get a negative is I'm going to take a negative divided by that positive. So y must be negative. So we had sine. Sine is negative, right? I realize my theta looks a lot like this. We've got a negative inside of a circle there, not a theta. Maybe I should use like a different color, huh? Sine was negative. Sine is y over r. This has to be positive. The only way I can make it negative is if this is negative. I know I'm repeating this a lot. I really want to make that clear. Okay. Cosine, that tells us something else. Cosine being positive, well, cosine is x over r. The only way I can get a positive out of that, again, the r is just irrelevant here. The only thing we're interested in is this x. Since cosine is positive, that means both of these had to have been positive, right? Positive divided by positive would give me that positive. So x must be positive. So each one of those told us a little bit of information. The first one told us that our y had to be negative, didn't tell us anything about x. The second one tells us our x has to be positive. So where is y negative and x positive? Where on our thing here? Our coordinate plane. X is positive over here, right? Positive here and here. Y is negative down here and here. So it looks like this is the one where both those things happen. So that's quadrant 4. That's what we're looking for. It has negative y values. It has positive x values. Right? So again, those are my positive x values. Those are my negative y values. That's where I have both. So play around with it, and I'll give you some homework problems on that. Not a terrible concept. But it is one that's important that you get here. Okay. Finally, let's see. Knowing how to find the signs of various trig functions is crucial for when you're given the value of one trig function and have to find the value for some other trig functions. I realize I'm just reading this aloud. That's because I sat down and wrote 3 sections of notes after playing with this video software for 8 hours. So now I'm going back and refreshing my memory. So we got to know. So this question asks us to find the remaining trig functions given this one trig function value, and they've given us some information about what quadrant that's in. So that's going to be important here. You know, knowing how these last two things we just went over. You know, they both focus on finding the sign, positive or negative, of our trig functions. That's going to be necessary in order to find each. And I'm not going to do all of them. I'll just do. I could just do 1 or 2 here. Because once you've got 1 or 2 of these down, you've done everything you need to find all the rest of them. Okay. So first off, they've given me a value here. They've given me secant is equal to -4. Right away, before I do anything else, I can use that to pick out a point that I'm going to use throughout this problem. No, we know secant, reciprocal of cosine, has got to be r over x, right? So this kind of leads me to an easy choice for what I should choose for r over x. If they give me a fraction, it'd be even easier. I'd choose the top of the fraction for r. I'd choose the bottom of the fraction for x. They didn't give me that, but look at this. Now I've got a fraction. So that gives me a really easy choice there, except I can't have r being negative, can I? I have to move my negative sign down there with that. Right. 4 divided by -1 is still -4. So that's what I'm going to do here. I'm going to let r equal 4. I'm going to let x equal -1. And again, I moved that sign down there because we've already agreed r is always going to be positive. So that's given me some information. Since x has to be negative, this thing's going to be in one of my quadrants over on the left. That has to be in one of these two, right? But this next bit of information, they tell us sign is positive. Sign is positive. Tell us that. Tell us sign is positive. Again, sign is y over r. So they told us that y has to be positive. This tells us x has to be negative. This bit from secant, that tells us y is positive. So that's quadrant 2. So we're going to need that information as we go along here. Quadrant 2 has positive y value, negative x value. Now, we chose an r and an x. How are we going to find y? Well, we're going to do it the same way we did the very first time we had to do this when we introduced these functions. We're going to use the Pythagorean theorem. Not to be confused with the Pythagorean identity. The Pythagorean identity has cosine, or sine squared plus cosine squared equals 1. Pythagorean theorem is this: x squared plus y squared equals r squared. So I've got some values for these. I know x is -1. I don't know y, so I'll just leave that one. I know r is 4. I can work this out a little bit. I get 1 plus y squared equals 16. Subtract 1, I get y squared equals 15. And then I take my square root, and I get y equals plus or minus the square root of 15. Because either one of those would give me this positive 15. But the reason we spent all of this time figuring out what quadrant we're in, that comes back and kick out one of my answers. In quadrant 2, I'm going to disregard this negative answer. Okay. So y could be, algebraically, y could be plus or minus square root of 15. In reality, in our problem here, we can't have this negative y value. We've already determined we're in quadrant 2, that's above the x-axis, our y value has to be positive. So that's why this is kind of crucial to go through all this rigmarole of figuring out what your sign is, positive or negative. It seems like a bunch of junk, but it's a little bit of thinking, a little bit of critical thinking, that will make sure all of your calculations are correct. So now that we've got our y value, I'll add to my little list here. Y is positive square root of 15. Now I can find each of those trig functions really simply using the definitions. Right? Sine is y over r, so that's square root of 15 over 4. Cosine is x over r, so that's negative 1 over 4, and so on. I'm not going to write out all of these because we've done all the hard work. Once we identify these three, then the rest of them just fall into place. Okay, so that's it for this section. So I'll see you next time.